Hi everyone, my name is Elliot McDonald, and today I'll be walking you through AMPL Tutorial 1. Cheminformatics data comes in many different forms that aren't directly digestible to our machine learning models. To account for this, we curate the data to ensure that chemical structures and properties are represented consistently. First, we're going to do an overview of how we do this curation process, and then we'll open up the code and do it ourselves. AMPL provides 5 custom functions to make cleaning your chemical data as easy as possible. Let's take an example here where we have our raw, uncurated data comprised of chemical structure strings called smiles. We have relations or sensors. We have some value for us to predict, in this case an inhibition constant. Then the units for these values. Note that an equal sign or a blank in this relation column means that the chemical has a Ki of exactly this value. But if there is a less than sign, it means that the actual value was less than the lowest value that was tested for the compound listed here, also known as left censored. Likewise, if the actual value is greater than the highest value tested, we will see a greater than sign, and it is called right censored data. For example, this second to last row shows us that for this particular smile structure, the inhibition constant is something less than 0.2 nanomolar. Our goal in this curation process is to standardize all of these as much as possible to make the model's job in predicting the Ki values from the smiles fairly straightforward. First, we will employ our first function, base smiles from smiles, which will allow us to take smiles from our chemical database and remove possible salt groups or isotopes from the string so that we are just left with the base, ignoring these extra details that the model doesn't need. In this example, we remove the sodium salt group and the isotope number on the chlorine. Next, we will use compute negative log response to turn the Ki's into pKi's, which helps stabilize the variations in the data in order to help the model more accurately find the trends in the data. And in this process of computing the negative log, we also need to invert the comparison operators, since if the Ki for CCOCl is greater than 5e negative 7 molar, then the negative log of its Ki is less than the negative log of 5e negative 7. In this step, we also make sure to convert our Ki based on the unit that it is given in, so that all pKi's are based on Ki in molar, not nanomolar or micromolar. Next, we will utilize the function standardize relations. You may have noticed that some of the relations in this table have quotation marks around them for no reason. And in the case of our last two examples with the comparison operators, we note that a greater than sign means the same thing as a greater than or equal to sign. So we can standardize all of these signs into one form. As with any data set, there are always outliers that must be removed, and so to address this, we employ remove outlier replicates, which identifies any compounds in the data set that have multiple entries, and if they do, it ensures that if any of them are outliers, they are removed from the dataset. In our case, the pKi of 1.505 is drastically different than the others, and thus it will get kicked out of our dataset. Lastly, we use aggregate assay data to combine those replicates that remained into one value using averages or maximum likelihood functions for those with comparison operators. Look at this final curated dataset compared to the raw data that we started with. We have standardized each of the columns of data and combined duplicate chemicals. Let's take a deeper look at each of these steps by visiting the code. The first step that we'll do is to import the basic libraries that we'll use in this tutorial: OS, pandas, numpy, matplotlib.pyplot, and seaborn. Once we've imported each of those, we can read in our data from the CSV that it was given in and convert it into a pandas data frame. We can check the shape of the data frame in order to find that the data set is comprised of 2,236 rows and 6 columns. Raw df columns values gives us a list of each of the names of these columns. We've seen 4 of the 6 of these before, but we'll also note molecule Chembl ID, which is the identification number used in the Chembl database, and then standard type, which specifies the type of measurement that we're looking at. In this case, the inhibition constant's Ki again. Now we can start running our data cleaning methods. We'll start with base smiles from smiles to remove those salt groups and isotopes and just get the base smile strings that we want. After importing our function, we can run it by just inputting the smiles column as a list and assigning it to a new column in the data frame as base rdkit smiles. Note that we also specified a number of threads called workers to help accelerate the speed of the function. Looking at the number of unique entries in both the original smile strings and the new base smiles shows that we in fact succeeded in simplifying some of the smiles. Next, we will call compute negative log response. Our data spans across many orders of magnitude, which makes it difficult for a machine learning model to handle variances which change significantly with the magnitude of Ki. So this pKi will make for a more accurate model overall. After importing the function, we call it on our data frame, specifying the column that the units of each value are in, the column for the value, the name of the column we want added with the new PKI values, the column with the relations, the unit string meanings for unit conversion purposes, and an in-place parameter that specifies whether we want the changes to be made to the inputted data frame or just as an output to the function. We can then graph the original Ki and the PKI as histograms to see their distributions. As you've seen in our examples from earlier, sometimes databases have different formatting when it comes to relations. Some databases can have less than or equal to signs when others just have less than signs, and some databases leave the relation column empty to mean the same thing as an equal sign. We call standardized relations to make all of the relations format the same way. The parameters that we pass in include our data frame, the name of the old relation column, and the name of the new column that we want the corrected relations to be put in. You may notice that we also name the chemical database that we are using under the DB parameter to help the function apply database-specific formatting changes. By looking at the counts of each type of relation in the old and new columns, we can see that we successfully standardized many of them. At this point, we have standardized the smiles, standardized the units, converted the Ki to PKI, and standardized the relations. All that's left in the data creation process is to use our last two functions to deal with any chemical structures that have multiple values in the database. Our first function of the two is remove outlier replicates, which will take in our data frame, the column with the chemical IDs, the response column, and the max difference threshold. The threshold is the maximum difference that we will allow a PKI value to be from the median of all the other PKIs listed for that chemical before we decide as an outlier and remove it from our list. We run this function and assign the output to a new data frame called curated_df. Once we've removed all of our outliers, aggregate assay data will combine all the multiple values listed that we decided weren't outliers. Since this is the last step of our curation process, this function has us input all the relevant columns from our data frame, and that way it will output a data frame with only the core columns that we need: the chemical ID, the smile strings, the relation, and the average PKI for that compound. The aggregate assay data has a lot of parameters, so I'll just go through each one quickly. The first parameter is just the input data frame that we got from remove outlier replicates. The value col is the column with our PKI values. The output value col is the name that we want to assign the column within the final data frame with the average values. The ID col, smiles col, and relations col are all their respective column names in the data frame. Label actives is a parameter that we can use to add a new column with a true or false value, denoting if the compound is active based on the average PKI value. We use that parameter for classification machine learning models, but we'll ignore it for these tutorials. Verbose just asks us whether or not the function should be telling us what it's doing as it's working. We can then print the original data shape and the curated data shape to see that our final curated data has significantly less rows as we combine duplicate chemicals and many less columns as we reduce the noise of our data to just the key columns that our model will care about. Finally, we can save our progress by saving the curated dataset that we've made to a CSV file, and that way it's all ready for tutorial 2 when we will split up our dataset into validation and training sets. See you all in tutorial 2.